Hi everyone. Thank you for joining. So I'm Yanju Chen. I'm from Veridice. So in today's talk, I'm going to talk a bit more about some of the most recent research and development from Veridice. So as you can tell from this title, we're talking about ZKSwift, which is a programming language for high-performance ZK circuits. So before I dig into too much details, I would like to probably share with you some of our most recent observations and insights or motivations about why we are doing this and what this is exactly solving, right? And as you can see, that ZK is taking off, and we can see ZK appearing in many different kind of places. For example, in privacy-aware apps, scaling, anonymous voting, and also in games. And then so this actually raises some of the questions for the developers here. For example, when you are developing some certain kinds of apps, you actually need to consider some kind of optimization of your ZK circuits over these kind of apps. For example, sometimes you need to, I think the most commonly thought problem is about how to improve the performance of your of the circuit, of the proof generation of the prover. And also in some other cases, for example, you need to think about whether for example, whether the circuit is running energy efficient, or whether it can be run in a different kind of hardware architecture, for example on a cell phone. So this actually raises a kind of great challenge for the developer. So this actually leads to our second observation. Learning ZK is actually hard, and it's actually becoming even harder for the developer to actually do the optimization here. So in order to write the ZK circuits, you need to be not only just be a programmer, you also need to have the crypto mindset here, in the sense that when you are constructing all those programming logics there, you also need to construct this kind of constraint logics there. But the good thing is that we have different kinds of mini DSL to choose from, which I can elaborate a bit more in the next slide. And then as Veridice is also auditing a lot of different kinds of ZK projects, we also realized that auditing ZK is actually even harder than writing ZK there, because on top of understanding what's going on from the circuit itself, you also have to have the mindset of doing security and doing formal verification in order to predict which place could be where could be the bug lies there. So all of these actually are pointing to something that is related to the design of the different kinds of architecture here about the language itself. So in this slide, yes, as you can see, there were two arrows. So I've just put some of the DSL for writing ZKs here. So for example, from the left-hand side of the arrow, I'm listing some of the high-level DSL here. So using those DSL, I think these DSL are kind of very user-friendly, in the sense that the user can just use this DSL, write some programs that she wants, and without realizing that, oh, I'm writing ZK, I need to consider different kind of constraints, and I need to consider a polynomial representation of all those semantics there. But on the right-hand side, those languages, those are kind of more lower-level languages, and then they are usually having a very steep learning curve there, where the user needs to understand a lot of lower-level details in order to actually start writing the circuits. But for those languages on the right-hand side, you actually provides more customizability for the user. For example, for those expertise. For those experts, they can actually perform very detailed optimization to change the circuit to fit into different kind of use case scenarios. So also on the left-hand side, if you look at the second arrow, actually from the phone verification perspective, we actually realized that for the left-hand side, those high-level DSL, they are pretty verification friendly. We can actually find it very easy to kind of write a summarization of those the programs written on those language and perform a very good verification with the highest security guarantee. So what we are actually thinking about is something that is lying in the middle. For example, somewhere near to this two in the middle, in a sense that you provide some language constructs that sit in the sweet spot that the user can find it easier to write, and also they could be easily connected to the lower level details about more optimization. But unlike these two languages, what we're thinking about is slightly different, in the sense that we also don't require the users just to write everything from scratch, all the details. We are using something that can automatically synthesize or search for or generate the intermediate IRs here that allows the user to just customize what kind of specs she wants. and then we do the optimization for themselves. So I will give you an example about like how we actually do that. But before that, so this is the like overall workflow of the ZKSwift architecture that we are thinking about, and then also we're exploring right now. So the first step is still, this means high-level DSL. So we actually start from high-level DSL. The users still continue to choose whatever high-level DSL they would like. And this is good for verification. And we have a compilation procedure that compiles those programs into our intermediate like IR. And in this IR level, we perform optimization and search, in the sense that the user specifies some objective functions. And then we perform those optimization of those circuits automatically for the user. So we generate the optimized circuits here, and we compile that into the low-level circuits at the end. So in this process, the user doesn't need to write any, or doesn't need to actually learn a lot about how to optimize everything. So we do that for the user. So there are a lot of different kinds of language constructs here. So I don't think I can cover all of the language construct, but I will cover one language construct that I think can be a pretty motivating example of why we need this and how we do the optimization. So this is an example here. It's doing basically converting a field element into different kinds of a sequence of bits there. And as you can see here, usually we just have defined, like, for example, 3 variables, and we have a for loop to kind of like do the to do the conversion. And eventually we have some constraints asserting that like a conversion is correct. So in, like, for example, some typical plonkish arithmetization, these kind of program actually will be compiled down and then generate different kinds of like a gigantic table. And then this table contains in sort of like intermediate computation trace that is required to actually generate the final like circuits here. So the message that I want to convey here is that in order to finish, so as you can see previous slides, you have suppose that we have like n, we want to convert a number into like a 16-bit array. And then here, for example, we need to have like 16 iterations. So for each iteration, according to the observation, if we do no optimizations, then it will actually generate a very large, like a large trace table here. And usually in plonkish arithmetization, if you have a large table, it usually means that you actually need to do a lot of computation, and your performance may likely drop. And then these actually generate a lot of, like, for example, 15 cells, if you count this number, 15 cells here. So there's actually room for optimization. So what do? So in our DSL, we introduced this high-level, high-order function called step. So what this step high-order function is doing is that it takes into a set of variables, and it takes into a function. So what it does is that I just like apply this function on top of those variables. And then again and again, and we generate a sequence or we generate a stream of intermediate computation trace. And by correctly filling into those different kinds of variables and functions, we're able to generate our intermediate representation that is equivalent to this original program, which means that these two, so this is a program in our DSL, this is the original program. They are doing the same thing. So what's the difference? So because F is actually corresponding to some kind of custom gates, so if we just unroll the DSL into its computation trace, we realize that we are actually consuming much fewer cells here, which means that we have achieved the same performance, achieved the same goals with even better performance because we're consuming fewer cells. So there's another missing piece here. So you may wonder, how do we do this? How do we translate from the original one to this one? Because obviously, in order to call this function, you have several like arguments to fill in, and there's no way, or it's very difficult for the user to fill in all those missing functions. So we achieve this by automatic search. So like kind of, if you're familiar with some kind of like most recent trends, you may realize that this is actually some like techniques in programming language community called program synthesis or like automatic program generation. So this is the overflow of the framework. So the user provided with the original program, which is the specification, and this is our DSL, and the user provided with the cost model. indicating what she wants to optimize. And then we invoke a search process that search for the best program represented in this DSL, which is actually best optimized for the user's goal. And later on, we compile this DSL, the program in this DSL down to the low-level program written in, for example, Zircon or Halo 2 or other kinds of low-level languages here. So by doing this, we are able to kind of like perform or provide an intermediate representation that allows the user to plug in any kind of optimization, which can also enable a different kind of like intermediate, like a search procedure that search for the best program that suits different kinds of needs. So there are other different kinds of insights about how we perform this search. For example, we can utilize the attention-based neural network to kind of align different program components between these two programs. For example, you can realize that actually to perform this kind of transformation, there are some part of the program constructs that are similar, or they share some like similar syntactic forms. So these are something that we can utilize those like heuristic-based search or this like data-driven way to help us complete everything. So just to wrap up, and then report something about our most recent dev progress. We've collected more than 7 circuits from production environment, and we already finished an implementation of a basic enumeration synthesizer, which means that we can actually have the tool running. And then we have observed some kind of like promising results here. Okay, yeah, so I think I'm running out of time, so thanks for your attention, and then I hope I bring you something interesting. And if you have any questions, feel free to reach out to our team, and then or we can chat offline. Thank you very much. Okay.
Yeah, that was an awesome presentation. I am always impressed with Veridice's presentations. That was no exception. We actually have a little bit of time for questions right now because we have a 30-minute break after this. So if anyone has questions, please raise your hand.
You use the name ZKSwift. Is it because it's like the Swift language?
No. So we thought of want to make it faster. So that's kind of a code name that we use. So if you have any preferred name, you can let us know. And yeah.
Thank you, exciting stuff. Wonder if it's open sourced on GitHub or, yeah.
We have open source plan, but it's still under development. So yeah, stay tuned, and then we'll, yeah.
Is the programming, the compiler can be run without the AI model? Like we can run it for ourselves?
So if I understand your question correctly,
can I do the stuff without your AI model? Because it looks like I have to depend on the AI model to do the compiling.
Oh, so okay. So the AI model here is just to serve as this kind of heuristic search. So you can imagine before this AI trend came up, previously in 20 or 30 years ago for the compiler optimization, they have different kind of heuristic functions there. So the way they mentioned AI is that the most recent trends here is that we can use AI to do better heuristic search, but you can choose not to plug it in and then continue to apply the enumerated search in a brute force way or any way you like. Yeah, it's extensible.
How to do verification in your language? Do I need to know some preliminary knowledge?
You can actually, yeah, good question. So you can actually do verification technically in different layers. For example, it's not showing the slides anymore. So there are different layers of language here. So we identified that the best layer to do the verification is on the the high-level language here, in the very first step there. Because in that step, the language they are concise and they have the specific kind of meaning, which is make it easier for expertise or for different kinds of people to actually formalize or get summarization of the mathematical representation, and then we can do formalization. But the intermediate IR language there is also pretty clean because most of the functions or components they are functional. So which are actually pretty good for verification purpose. So both two levels are good. But if you like, you can also do verification on the very like a low level, which could be kind of like an engineering like effort driven, but it doesn't mean that it's not doable. So the preferred way to do that is like you do that on the high level first, if it's possible, and otherwise you can do it in the intermediate level, which is also good. And the last choice would be so basically all levels are good, but the first two levels are preferred.
In the one slide, you said you compile to an IR. Do you compile, what proof systems are you compatible with? Is it just Halo 2, or is
it's kind of more generic proof system. Like it supports different kinds of, so our goal is to design a DSL that supports different kinds of like proof systems. It's just like kind of something like an LLVM version, like this. Yeah, a user is allowed to extend the different like, compilation directions into different kinds of proving systems. That's our goal here. And currently we support like actually Halo 2 and also like Circom. And we're adding more to that. Yeah.
All right, awesome. Let's give it up for Yanju one more time.
Thank you very much.